Coming to my talk, Abstractions for Program Analysis. We did have a little bit of technical difficulties this morning, so there's going to be a little bit of formatting issues here. I apologize for that. But we're going to be talking a lot about programs today and abstractions. But nothing's going to be specific to any one programming language, operating system, or architecture. At points, we won't even be talking about code when we're modeling systems for analysis. But that's getting a little bit ahead. We're going to be looking at programs in a number of different ways that make it easier to answer the questions you care about. So if you're in the right place, you're some sort of engineer who works with code. Whether you write JavaScript or you're exploiting the Linux kernel day to day, I'm going to help you better understand the systems you're interfacing with. But let's make sure that we're all on the same page. Since we're going to be talking a lot about programs today and abstractions, let's start by defining those. Should be easy, right? We're all engineers. We work with programs every day. We should have a pretty good idea of what they do. So how would you define what a program does? Usually the first answer I get is more procedural than it is flexible. Something like they execute a list of instructions. But is that accurate? Is that just as apt of a description for an LLM versus a script? Aren't LLMs bad at following our commands? Don't processors execute our instructions out of order? Aren't there side effects and aren't there bugs? So I tend to prefer this definition. If they couldn't manipulate data, then the entire system would only have one state. And if they couldn't move data, we couldn't change between states. So we're only on slide 3, but we can already abstract a program to its list of commands and inputs as just moving and manipulating data. Or we can think about a program as the states it can be in and the transformations among those states, which is how fuzzers view programs, because fuzzers try to find all the states you shouldn't be able to get into in a program. Not just invalid states, but invalid edges between states, which is effectively the same as tracking the data for the program, because the state of a program is just the values at different points. So, program analysis, don't lose my mic, is just the study of how data are moved and manipulated. And this holds true because early program analysis's main concern was to optimize code through removing excess calculations and trying to keep the data in one spot. But it's important to remember that program analysis is actually a field of mathematics. And those mathematics tell us that everything we want to do is generally impossible, which is often referred to as the full employment theorem for program analysts, but we shouldn't rely on that too much. Often these problems are postulated in imaginary spaces, and they often break down when applied to real systems deployed in the real world. I'm going to argue that we just need abstractions that capture the context to make those problems decidable. These systems aren't floating out in space, and actually that would be worse, because then we'd have to deal with random bit flips from gamma rays and stuff. We have to understand that these systems are working in the context of everything happening around them. Which is why this abstraction is one of my favorites these days. I jokingly call it the standard model of program analysis. When we think about how data can flow among points in a program, everything the compiler, reverse engineers, vulnerability researchers, and even you guys do when trying to understand code decomposes into 4 trivial queries. And another abstraction for you is that it fits on 2 axes in a nice little square. Those 4 questions are simply, may something happen before you, may it happen after you, or must it happen before you or after you? Now, these 4 algorithms are real, they have names, but they're not important. So let's take a look at this in context of some code. On line 9, I'd like to be able to verify that my function was initialized correctly. So we're going to be doing a forwards may analysis, since we want to know what the values may have been before line 9, and because I can see 3 paths through this function from definitions to the return site there. Now, to be able to automate this, it can be quite arduous, because we're going to have to scan the text for return, we're going to need to process its arguments, we're going to need to determine if it's a constant or a variable. If it's a variable, we need to scan the text for other instances of that token. Then we need to keep track of uses and writes and order and branches. You're basically writing an entire compiler. And now, The bad news is that's unfortunately what you need to do. Hopefully, you're not writing a compiler every time you analyze a program. Hopefully, you're using a program analysis framework that provides it for you. But it needs to be done. And as long as it's being done either by you or by the program analysis framework, one little trick we can do along the way is to give numbers to each explicit assignment. And when we do that, we then encounter the problem of which version do we return? Do we return 1, 2, or 3? In fact, we need some way of representing that we can return any of them. And we do have a way to do this, but we need a little bit help. We need a little helper. So revealing Feline and Fido. Their namesake comes from the Greek letter phi or phi. Both are correct. And it's a function that statically merges all possible states of a variable. So at line 9 there, it's just saying result 1 can be either function 1 or function 2 or function 3. And by introducing phi, we've gotten to one of the most popular abstractions used in basically everything. This is SSA, or single static assignment form, because every variable is defined in one spot. This is really helpful for tracking data flow, and it's basically exclusively what LLVM uses. Because now it's super easy to see that the value of result 1 may be none. Algorithmically, all we're doing is we're iterating through all the variables that contribute to the definition of result 1 and ask, is this none, is this none, is this none, which is just a for loop or a call to map or an any call, whatever it is in your programming language. And with multiple exits, you just nest that loop for each return variable. And now, what I admire about this technique is the subtle brilliance in it, because it reduces a lot of the questions we care about into parallelizable Boolean queries that you can throw into some set math. And then the answers to most of the questions we care about just turn into whether none, some, or all the elements in a set are true. So, actually, it's all Boolean set math. And if we're creative about how we combine these queries, all sorts of bug classes fall right out. So at variable use sites, if we may initialize a variable before, but not must, we have some uninitialized variable use on some path. At dereference sites, if we may initialize a variable before, not must, or we may be null before, we may have a null pointer dereference, but we still definitely have an uninitialized variable use on some path. And at calls to free, if we may use the variable after, you might have a use after free. By asking different questions at the same locations, we can expose different bug classes. And by asking different questions at different locations, we can find the same bug classes with different levels of precision. You can also chain queries to extract properties, and you can use them to find if unsigned subtractions are properly checked. And just for giggles, I throw in the solution to the halting problem as well, which is famously unsolvable, but there's a best abstraction for every problem you could want to solve. Depending on how you've been counting, if you've been counting, we've already seen 7 or 8, and I'm not making any of these up. Nothing here is novel. We've known about all these problems since the 70s, the 60s, and even earlier, and we know a lot of their solutions too. But the state-of-the-art program analysis frameworks are in many ways 30 years behind the state-of-the-art research. There's a lot of research out there that they just have not yet implemented. And what I've compiled here for you today are some of my greatest hits I think everyone should know about. So for the rest of this talk, we're going to be exploring more abstractions. We're going to see how they're going to be useful. But I also want you to walk away understanding the shapes that these abstractions take, how you might choose to reach for one, and what actually makes for a useful abstraction for program analysis. So what got me into this? My name is Kyle. I was one of the original interns at Vector 35. I've been able to touch just about everything in Binary Ninja over the years, which is great. Or recently I found myself on the training train, which is great because I get to think about how to distill some of the most interesting and at times some of the most chthonic looking concepts into something for engineers. I was wishing you could see this whole thing. This is the Galois connection calculus for abstract interpretation by Cousseau and Cousseau. The reference there got cut off. This is the same thing as the square from before. And I think you'd rather read it that way than through the calculus there. But this lets me help see things through new perspectives, which in turn inspires new research, new plugin ideas for Binary Ninja. And there's so many problems to solve, but we believe in engaging with the community, getting your feedback, and seeing what we actually need to implement. And I also have some hobbies. I'm fortunate enough to work in an area, work remotely in an area where I can be on the slopes of mornings. So I work for Vector35, who makes a decompiler, disassembler, debugger, and binary analysis platform you may have heard of before. We're about 20 strong now. Roughly a third of us are remote. And the office itself is down in Central Florida, close enough to NASA to watch the rocket launches. But we were talking about definitions, and I got a little bit carried away. So let's start from the beginning again, but this time we won't stop asking questions. So, what do programs do? They move and manipulate data. And what mechanism do we use in source code to describe those data? You literally define the structure of your data using types. And how do you describe how those data are allowed to interact? In some languages, you literally define your operators. But in most other programming languages, you define functions that are allowed to operate on those data. Think private and public member functions of a class. And some programming languages will only allow the same types to interact, whereas other languages will bend over backwards to let any or to not throw type errors. We're just going to let that dangle. All right. So what's a type? It's its data and an exhaustive set of rules for how those data are allowed to be transformed. If something is valid, the semantics, the meaning of that transformation must be defined somewhere. And I think that people forget this, which is why I often get that answer, that bad answer from before. Two types may have a function that allows them to, for example, add, but they also may not. And it's when the compiler runs out of transformations that it may apply in a given state when it starts to throw an error. Because it can't know what you're trying to do if you haven't defined the rules for how to do it. Which is a fancy way of saying that you need to define the semantics of your program through types as well. Since again, that allows you to constrain both the data and how it's being transformed. So, one last time, say it with me this time. What are programs? Programs are types. And this should make sense because, here we are. We have object-oriented programming languages. Since all programs do is move and manipulate data, and we describe those data with types, we describe those movements with types, we describe those manipulations with types, we can describe entire programs as types. And again, the states themselves aren't too interesting. Data by itself is rarely dangerous. It's how that data is moved and manipulated that we care about. It's the semantics of it. But the type theory here goes really deep. Types, in many ways, are the ultimate abstraction for program analysis. But we need to talk about how we get there first. So, types define the semantics, but it goes the other way around too. To be able to determine the types of things, you need to be able to understand how they're used. Their semantics, and I'm going to define semantics as the meaning of code. But so if semantics are the meaning of code, then what is the meaning of this code? A little bit of assembly there for you. We're moving 12 into AX. And now, it kind of depends on what 12 is. Is 12 a pointer? Is 12 an offset? Is 12 an amount of money? Is it a height? Is it something else? We can't know. We need more context to understand what this is trying to do. Assembly instructions by themselves are kind of meaningless. They don't have intent baked into them. And now, engineers sometimes get upset at me for saying this, because they're like, no, the semantics of that are definitely that it moves the bits of 12 into the A register. But that's only true if you're a emulator engineer. You only care about the execution characteristics of the instructions, not the semantics, not what it means. As program analyzers and reverse engineers, we care about why things are happening the way they do. We need a higher level understanding. So, if we go up to C and we take a look at this, what's the meaning of this code? I'm still going to argue it's not much. C does not have that strong of a type system. We can still use this as a pointer, an offset, a height, an amount of money, any number of things. It is a little bit less than C, assembly, what it can be. But is it further constrained if I tell you that X is an integer? I'm going to say no, because you can still convert integers. What if I told you that this was happening in a loop? Then we're starting to get somewhere, because maybe we're iterating over pairs of elements. And then finally, if we keep going and we go up to Rust, Rust has a very strong type system. There we go. Since we can see that C is an integer, we know that A and B must be an integer. This is not going to be a function pointer. It can still be an offset. It can still be an amount of money. It can still be a number of other things. But it's definitely less things than C, and it's definitely way less things than assembly as well. So these are the promises our programming languages make to us with their type systems. The stronger the contracts, the stronger the meaning of the code, the better we can understand it. Now, when working with abstractions, context is king. You can try to translate ad hoc without context, but realize you very well may end up with a mess. This image is courtesy of Google Translate, which if it had realized I was trying to figure out the flavor of a candy, hopefully never would have translated the ingredient list like that. But again, we're working in the real world, and when we're analyzing systems, we need to define scope. You could model gamma rays flipping random bits, but do you need to? The most accurate model of a program might be a universe simulator, but that's not going to be easy to write, and that's not going to be easy to work with, and it distracts from the problem at hand. So instead, by looking at problems differently, by zooming in or zooming out, by throwing away or changing our base assumptions, we change the semantics of the system. A question that's impossible to answer in one semantic scope might be possible to answer in another. And we lost the image, but this is an XKCD solution to the halting problem, where he says, can halt return true? And it's funny because you shouldn't assume that a program will always exit. That's the basis of the halting problem. You cannot determine whether a program will run forever or eventually halt. But in the real world, I think it's safe to assume that someone will eventually forget to pay the power bill and the program will eventually halt. So by changing our semantics or semantic scope is exactly what we're doing when we're changing between abstractions, and it allows us to answer questions that were previously impossible. But when you're choosing an abstraction, there are some trade-offs. Do you want a very simple instruction set that abstracts all 30 different mobs into one type of assignment? Or do you want to have an explicit instruction for every mob in x86? You would make a IL that's very easy to lift if you have one-to-one instructions from your assembly to your IL, but then it becomes hard to parse as an analyzer because you have to have thousands and thousands of cases for every different type of instruction. Now, of course, you do have some trade-offs there because if you only have one assignment type, maybe there are some types of mobs that have side effects that you can't model. You could go further. You could have maybe even a single instruction type for everything you want to do that has maybe some optional fields that aren't populated when they aren't used. Or again, you can have a explicit instruction for everything you're trying to do. There are more trade-offs though. Do you want types? Do you have type information? If you don't have type information, do you want to have to recover that type information? How do you want to represent side effects? And there are a lot of weird machines out there. So how flexible do you want to be for bizarre architectures and bizarre languages? ILs are not usually something that are looked at. They're behind the scenes. They're in the belly of the beast. So let's take a look at them. This is a list of most of the ILs used in reverse engineering for program analysis. But there is a big one missing here. You might notice it if you look closely. It's LLVM. Because these are all the abstractions, that use LLVM. There's a lot of them in here. But there's even more than that, because there are flavors of ILs. You think of LLVM as this monolithic pipeline that compiles any source code language into any architecture. But actually, depending on the architecture you're targeting, the LLVM, that bitcode that Clang emits, will look very different. It has intrinsics, it will pack arguments differently. There are a lot of things that LLVM's main analysis pipeline keeps specific for the different architectures throughout the analysis. And this is true of our program analysis frameworks as well. In Ghidra, we have low P code and high P code. And even IDA has microcode that goes through several iterations of optimization before they finally emit their decompilation. Let's take a look at that. This is IDA Pro's microcode, the first step of emitting it. You can see the top 4 assembly instructions there get turned into all those microcode instructions. They only have 72 instructions, so you have to expand some of your x86 instructions, because you have thousands and thousands, into multiple instructions. But then they optimize. They fold a little bit, they fold a little bit more, and then eventually we get to something that I would never want to read and never want to write an analysis script over. I can't even tell what that's trying to do anymore. It's just too hard to read. Darn, we lost the P code slide too. But Ghidra has a similar concept. There's instructions that fold into or unfold into many more instructions, and eventually it turns into one instruction. What's nice about P code is it is actually a little bit more readable than microcode. Their final result value is better. Come see me after the talk if you want to see that slide. And then we have real as well. This is an example of a very reduced instruction set. We have a simple instruction which turns into 19 instructions there. Again, probably easy to write a program analysis script for, because you only have 17 cases you need to handle. But you're going to need to be processing a lot of nodes. So you sacrifice ease of development for, I suppose, compute time. And then this is what Valgrind and Anger uses. This is on the far opposite end of the spectrum. They have thousands of instructions. It's not RISC-like at all. And even despite that, they still have simple instructions that unfold into multiple ones. Because of that trade-off square from before, and as well as programmers wanting to be lazy, we tend to see a trend of tools using the most basic representations for code they can get away with. And there is a formalization for this. We call them normal forms. Normal forms are irreducible. Assembly is really close to normal form, which is part of the reason that compilers love normal form. But assembly instructions also can do weirder things. You have your LEA instruction, which has a multiply, a left shift, and an addition in it, all in one. But they can start from the normal forms and then sort of fold those together to get to the instructions that they want. What's nice about, well, there are rules for these forms. This one is called a normal form. There are different types of normal forms. There's also conjunctive normal form, disjunctive normal form, a whole bunch of other ones. But the ones that most of our program analysis frameworks use is going to be a normal form. And in a normal form, all arguments are a variable or a constant, and all compound statements have been simplified. And this is what it looks like. You start with a line of code that looks like on the left, and you turn it into what it is on the right there. What's nice about this is every intermediate value is named. Evaluation order becomes explicit. You no longer have to remember your order of operations. Small instructions are much easier to analyze in your scripts. You don't need to recurse through your sub-expressions there. And we can analyze these normal forms to find patterns that fall out. Because we're normalizing things, we're reducing it to a fairly basic representation here, we'll see lots and lots of really useful patterns that come out of this. You can recognize structure member accesses, you can recognize array accesses just by looking at the ILs. But we can take this a step further. Once we have our normal forms, we can impose some additional rules onto them to make them even more useful for program analysis. So in SSA, all variables are read-only, and future reassignments are now new versions. And this is what it looks like. We've already taken a look at this. But wait, you need to reuse variables. What do you return here? We've seen this before too. We just need to introduce phi. We just need to be able to say result 3 will either be result 1 or result 2. But wait, you need to reuse variables. What do you do in this case? Do you have to unroll the loop? I'll give you a hint. The problem is on this line here. Oh, there we go. Right there. We know that we will need to create at least one new version, so we can throw that one in there for you to start. But we're still left with the question of what we're doing on line 2 there. We need Feline and Fido to the rescue. And what's important to remember here is that static is not the same as const. Const is a value that does not change. Static is a single definition that remains valid throughout its lifetime. So remember what I said. Phi merges all possible states. And version 2 here is defined recursively. One thing that people tend not to like when they first see this is they're like, wait, Kyle, you're using I version 3 before it's defined. But it's important to remember, these are not new variables. They are new versions of variables. The variable was defined on line 1. And on the first iteration in that loop, the phi will always resolve to I number 1. I2 will become I1, which is 0. And then I3 will become 0 plus 1. And then we'll go back, and I2 becomes I0 plus 1. These are both defined recursively, but they have a single static range of values. The values of these variables are allowed to be ranges. All right. So, in SSA, we have every variable has one definition, so this makes it really easy to build use def chains. We can simply find the definition for a variable and iterate through all of the variables that contribute to its definition. So if we look at this in code, we start with a non-SSA form of a code snippet on the left. We turn it into the SSA form in the middle there. You can see that we're returning C1. So where's the definition for C1? It's there. What is the value of C1? Well, it's B3 times A1. What is B3? What is A1? A1 is input. B3 is either B1 or B2. What are those? Those are A1 plus or minus 1. And A1 itself is the input to the program. So if we turn those into chains, we start to get what's all the way on the right here. You start with your return C1. You substitute in the variables that contribute to its definition, and then you keep going. You plug in that it can either be B1 or B2. B1 or B2 is A1 plus or minus 1, and then you can throw the input in there as well. And now we have a nice little formula for the value of this function. And we can represent that through graphs. SSA is super, super powerful because it allows us to do these forward data flow analyses. You start from all your sources, and eventually you trickle down to the one point you care about. If you start to track backwards, from the bottom to the top, you get path explosion. You can notice here that the definition of the variable we care about at the bottom there, R11 underscore 1 number 2, is actually coming from 2 function calls and the argument to this function twice as well. So then you need to recurse into those functions, see everywhere that this function is called, and as I said, path explosion gets crazy here, tracing backwards. So we have somewhat better representations for this. Since SSA is only tracking the definitions of variables, there's more information we can capture at use sites. SSI, which stands for Single Static Information, starts in SSA form, where the phis are merging variable definitions. But at branches, sigmas, split uses. So if we start with the non-SSA form of the code on the left, we turn it into the SSA form in the middle, where we have our phi merging variable definitions. And then we can turn it into the SSI on the right, where we're inserting A2 here and A3 to represent the value of the variable at use sites. So in the first branch, we know that A1 will always be greater than 1. And in the second branch, we know that it'll always be less than or equal to 1, which is great. But then we do need to merge those variables again after the branch with phi. And again, by doing this, SSA or SSI, we can do our full forwards, backwards, may, and must analysis a little bit easier than we could on SSA alone. Now, it is worth mentioning, basically no program analysis framework out there implements SSI, but I've heard a lot of them talk about that they probably should and eventually will. All right. So, that brings me to my conclusion. I would like you guys to stop writing compilers, please. When you're trying to analyze programs, stop parsing the assembly, stop trying to figure out your operands and what's being written to and read from, and start using tools that give you adequate abstractions to answer those questions instead. Ideally, find a system that allows you to add your own abstractions in there. But more than just generate them, high-fidelity transformations among representations would be the true ideal. Because there's a correct abstraction for every problem you could want to solve. More and more, I'm seeing tools with flavors of ILs, but I'm going to argue that this is an anti-pattern. If you have an IL that's in a partial state that's not fully filled out, we're not looking for one IL to rule them all. We're looking for specific abstractions, specific representations for the specific problems we want to solve. So, thank you for listening to my talk, Abstractions for Program Analysis.
We have the time for one quick question, if you had one. So,
Thank you for your talk. I just have only one question about something you said about LLVM IR. You said that it could be different between architectures. Is there a specific reason for that? Because as far as I know, its whole point is just to make it more, well, keep the representation similar between multiple architectures.
So the question is, why does LLVM have flavors of ILs, basically? The Clang is trying to pre-optimize the code. It knows the target architecture that you're trying to target, and it has heuristics built into it being like, this source code pattern is for sure absolutely most optimally compiled in this way. Don't do the analysis pipeline, just use our table of heuristics effectively.
so we can thanks again Kyle for his code.
Thank you.